The NS equation is highly nonlinear because it has this thing, right? This thing is very hard to deal with. So if you say you want to solve for the NS equation to get a general solution of it, well, be my guest. But I think no one in the world has managed to do that yet. So if we want to get some solutions of the NS equations, we need to make many assumptions in order to simplify the cases. And also we need to introduce some special boundary conditions. So I'll tell you some particular solutions of the NS equations here. Particular solutions of NS. Our first big category will be called the steady case. Steady, we know, it means that the circumstances of the fluids doesn't change with respect to time, right? So every property's time derivative will be equal to 0. Okay? So the first small case, I think, is a case that we are all very familiar with, which is parallel plates. I guess actually this is the first kind of laminar flow you have ever encountered in your fluid mechanics study. Let's say we have two plates. The lower plate is not moving, but the upper plate can move. Let's say it may move with a velocity u. The distance between the two parallel plates is h. So what's the flow in here? The fluids are here, right? Well, what is the flow going to be like? This is what we call to be the Couette-Bossuet flow. Couette-Bossuet flow. Okay, so let's assume the fluid here is incompressible. Okay, so we can simplify the continuity equation, right? The continuity equation becomes the divergence of velocity equals to 0. du1 dx1 plus du2 dx2 equals to 0. Here I have two ways to simplify things. The continuity plus one assumption of mine can give us a simplified result. Let's first make the assumption that the flow is fully developed. Okay, suppose fully developed. What do I mean by fully developed? The velocity profile on the upper stream will be exactly the same as in the downstream, right? So it means the velocity profile or the u doesn't change, the u velocity doesn't change with respect to the x1 direction, right? So it means du1 dx1 equals to du2 dx1. Everything doesn't change with x1. Well, not everything. I mean the properties of the movement of the fluids, right? Which are manifested in the velocities. So du1 dx1 equals to du2 dx1 is 0. Okay? So if we have this assumption, then du1 dx1 equals to 0. We have du2 dx2 equals to 0, right? du2 dx2. This thing must be 0. But if du2 dx2 equals to 0 and also du2 dx1 equals to 0, that means u2 doesn't change with neither x1 nor x2, right? This means u2 can only be a constant. So we have the conclusion that u2 is just a constant. And what is this constant? Well, here we need to introduce a boundary condition. Let's observe the lower plate, okay? So for the lower plate, can it can it have a U2 here? Can a fluid very near the lower plate have a U2? I think it cannot, right? First, it cannot have a U2 downwards because the boundary here is a solid boundary. If I have a U2 down here, then there's penetration, right? We don't allow that. Also, we cannot have U2 upwards. Why? Because here in the middle is full of fluids, right? If there is a U2 upwards, then here will be vacuum. So this either of the cases we cannot allow, which means the U2 near the boundary, which is when x2 equals to 0, when U2 equals to 0, this thing is 0. So we know if at one point the U2 must be equal to 0, then the constant U2 is just 0. So what have we learned? We can only have a velocity in the x1 direction, right? Which means we can only have U1, but we cannot have U2. So the flow is what we call to be one-directional flow. One-directional flow. Okay? This is one way to simplify things. Another way, let's make another assumption. We directly make the assumption that the flow is one-directional. Suppose one-directional. So from the assumption now, we get the fact that U2 equals to 0, right? So now we have U2 equals to 0, then the U2's derivative must be equal to 0. So we have du1 dx1 equals to 0, right? du1 dx1 equals to 0. And what does this mean? Fully developed, right? The u doesn't change with x1. Neither does ur change with x1, right? Because ur is constantly 0. So we still have the same conclusion, which is the flow is fully developed. So actually, to be exact, we have two ways to simplify things, but they will yield the same result, right? We can either assume the flow to be fully developed, and then we get the flow is both fully developed and one-directional. But we can also do it backwards. If we suppose the flow is one-directional, then we can also get the fact that the fluid here is one-directional and fully developed.